Greetings, math fans. All right, so this is related rates problems here, and it's page 251 to 253, numbers 11, 16, 17, 28, 29, 33, and page 258, number 46. All right, and again, they're all related rates except for the last one, I believe, is optimization problem. So let's just start out with number 11 here. I'm going to read this problem real quickly here. It says inflating a balloon. A spherical balloon is inflated with helium at a rate of 100 pi cubic feet per minute. And this is A. How fast is the balloon's radius increasing at the instant the radius is 5 feet? So this is the deal. First of all, they give you the rate that's inflating. All right, so that, and you can even tell that it's change in volume over change in time because it's feet cubed per minute. So that means I know my dV dt is equal to 100 pi cubic feet per minute. Okay, and then for A is I'm giving you that R is equal to 5 feet. Okay, you guys, maybe you don't know, but I'm going to tell you the volume of a sphere is 4/3 pi r cubed. Okay, and obviously that's the formula we're going to be using. And we're going to take the derivative of that because we're given dV dt, and we're looking for, because it says how fast is the balloon's radius increasing. So what we're doing is we're looking for dr dt, right? Change in radius with respect to time. All right. So let's take the derivative of that. V is equal to 4/3 pi r cubed. The derivative of V is 1, of course, and then dV dt, right? And then we have 4/3 pi r cubed, which is just going to be 4/3 pi, right? That's just the constant in front. And the derivative of r cubed is 3r squared, and of course, dr dt. Okay, so these threes cancel here. It's kind of nice. Let's plug some stuff in here. We have dV dt. This is 100 pi. I'm going to leave the units off now, just so it's a little bit easier to plug in. So 100 pi equals 4 pi, and r is 5 squared, dr dt. Okay, so we have 100 pi equals 5 squared is 25 times 4 is equal to 100 pi. Ooh, that's a lot of pi's. Dr dt. Hey, sweet, look at that, man. Dr dt is equal to 1. And of course, what are the units? It's radius, right? Radius with respect to time. So it's 1 foot per minute. Don't forget your units. All right. B, let's just put B right over here on this side. B asks you how fast is the surface area increasing at that instant. So surface area of a sphere, if you don't know that, you should have looked it up. But it's 4 pi r squared. Okay. And so what we're going to do is, it's kind of the same idea, but they're saying how fast is the surface area increasing at that instant. Take our derivative, right? It's the derivative of surface area is, we'll call it just S, because it's just a little easier, so how about get rid of that. So it's derivative of S is 1 times ds dt, just like normal here. And then we take the derivative of this, so we're going to get 4 pi, derivative of r squared is 2r, and then dr dt. Okay, and so ds dt is equal to 8 pi, and then r is 5. And we know dr dt, don't we? And some of you are saying, well, wait a second, Mr. Curvis. No, we don't. This is a different problem. But actually, it doesn't matter. We know the rate of change of the radius at the time. It doesn't matter if it's surface area or volume. We are going to use this information right in there, from there. Okay, because it's still change in radius with respect to time, no matter if we're talking about volume or surface area. It's still the radius is still changing the same. Okay, it doesn't matter what we're talking about. So it's just kind of nice we can use that value, which is 1. And then, of course, we multiply everything together here. And we get ds dt is equal to 40 pi. And then it's feet squared per minute. Okay, because you notice, right, the dr dt, that was feet per minute times another r, which is another foot, right? So that's why it's feet squared per minute. Okay, and that's how you do B. All right, let's move on. So you kind of just see we use some of the information from before because, as I totally stressed again, I know it's kind of weird maybe, but this dr dt and this dr dt are exactly the same. It's still the change in rate or change in radius with respect to time. All right, number 16. It's a growing pile of sand. It's very exciting. It says sand falls from a conveyor belt at a rate of 10 cubic meters per minute onto the top of a conical pile. The height of the pile is always 3/8 of the base of the diameter. And then it says how fast are the A, height, and B, the radius changing when the pile is 4 meters high. Give your answers in cubic or in centimeters per minute. So let me erase this here. This is what you have. You have your cone here, your conical pile. Try to draw a little 3D picture there. And they give you a little information. First of all, they tell you that the height is 3/8 of the base diameter. So height is 3/8 of the base diameter. Okay, and let's put that in diameter here. Okay, so they're telling you that the height of the pile is also 4 meters. So the h here is 4 meters. Now, this is the deal. First of all, they're giving it to you in terms of diameter. And really what we need to do is, we're going to use a nice little friendly formula here. For the volume of this cone is 1/3 pi r squared h. All right, and what we're doing is we're trying to find dh dt, that's A, and then B is dr dt. Okay, so change in height and change in radius. All right, so the first thing I want to do is I'm going to use this formula here because remember, guys, when we do related rates, it's nice to have all the variables all given to us and change, all the different derivatives and everything, but we're only given certain things here. Okay, in fact, we're given dv dt, right? It tells you right in the beginning of the problem it's falling at a rate of 10 cubic meters per minute. So it's 10 meters per minute. And I don't have enough information to have both the r and the h, so obviously that's the reason they give you h is equal to 3/8 of the base diameter, is then you can come up with some relation between the height and the radius. Now, first of all here, your height is, this is a little tricky, it's 3/8 times the diameter, or 2r. Do you guys agree with that? So really my height is equal to, if I simplify that, it's 3/4 r. Okay, that's good, and then I can turn that into r is equal to 4/3 h. So there's another friendly formula I can use, right? All right, so let's do part A here first. Okay, we have our volume is 1/3 pi, and then instead of r, we're going to do 4/3 h pi r, and that's squared, and then times h. So let me rewrite that. It's going to be, put all together here, I get 16 pi h cubed over 27. Okay. So now it's really convenient because now I am looking for, right, part A was dh dt, that's why I'm looking for that first, and now I've got, it's all set. I just have two variables here. I take the derivative of the left side, and that's just dv dt. And I take the derivative of the other side, and that's going to be 3, right? Derivative of h cubed is 3, and that's 16 pi, and then h squared over 27. And then, of course, is then dh dt. All right, and let's kind of move down here a little bit so I can fit everything in. Let's plug everything in. dv dt is 10, is equal to, I can cancel a few things out here. It's 1 and a 9. All right, so we get 16 pi over 9, and h squared, h is 4, right? That's what's given, so it's times 16 dh dt. All right, so it's just, oops, this is a 9 here. Okay, and then just got to divide it out. It's all algebra here, and you wind up getting dh dt is equal to 45 over 128 pi. We're giving an exact answer, and this is meters per minute. Okay, but in this case here, what they're doing is they're asking you for centimeters per minute, so you got to be careful. So you're going to multiply that by 100. So you wind up getting 1125 over 32, just simplifying it. And you can put that in your calculator, right? That you can just use your fraction button, of course not having pi in there, and get 1125 over 32 centimeters per minute. Okay, that's the answer A. Yeah, it's kind of a little complicated here, but not that bad. Let's look at part B. You could do the whole thing and substitute instead of having h in here, you substitute all back into have r in there. But remember, math fans, this is dh dt right here. That's dh dt. So why do I need to take the derivative all over again when, let's go back on top here. Do you guys agree that I have one of my relations here is this? R is equal to 4/3 h. So let's write that out. It's very exciting. R equals 4/3 h. All right. My change in h with respect to time, it doesn't matter if I find it using the volume or if I find it anyway. It's still my change in height is still the same. So what I can do now is have R is equal to 4/3 h. I'm going to take the derivative of both sides. So I'm going to get dr dt is equal to 4/3 dh dt. That's pretty sweet. I've got dh dt. So we're good to go, man. Dr dt equals 4/3 times 1125 over 32 pi. Okay, and if you simplify that again using your calculator with the fraction button, you get 375 over 8 pi centimeters per minute. And by the way, if you would get just a decimal here, it's about 11.19 for A, centimeters per minute. And this guy here is about 14.92 centimeters per minute. Okay? So this just kind of shows you don't have to do all that work all over again with volume. As long as you know one of the, derivative of one of them, and you have a relation between R and H, I just use that derivative again. Okay, that's kind of handy. All right, let's try the next one here. Number 17 says, draining a conical reservoir. Water is flowing at a rate of 50 cubic meters per minute. Okay, so right off the bat, I see its dv dt is 50 meters cubed per minute. Pretty easy. From a concrete conical reservoir, vertex down. So this is kind of what it looks like here. All right, and I have, this is my couple pieces of information here. It says a base radius of 45 meters. So this is 45 meters. and a height of 6 meters. Definitely not to scale. Okay. How fast is the water level falling when the water is 5 meters deep? Okay, so basically, I want to know when h is equal to 5. I'm wanting to know how fast is the water level falling. Okay, so I'm looking for dh dt, right? How that height, what's the or how fast is it falling is the height of it. How fast is the height falling? Okay, so of course we're going to need our nice little friendly formula here. Volume of that cone is going to be 1/3 pi r squared h. And once again, we're given dV dt is equal to 50 meters cubed per minute. Okay, and so A is going to be find dH dt. Okay, so let's write out here volume is 1/3 pi, and what we're going to do here is similar to what we've done before, right? With this is a right triangle, finding similar triangles. Do you guys agree with that triangle that we have here, that 45 and 6 triangle? I can write my r here, my h, and then I can relate those two. So isn't it r over h is equal to 45 over 6? So 6r is equal to 45h. So r is equal to 15h over 2. Because I need it in terms of h, because I'm looking for dH dt. That's why I'm solving for r, so I can substitute that back in there. And so it's 1/3, and then it's 15h over 2 squared times h. So simplify this before I take the derivative, and I get 1/3 pi 225 h cubed over 4. So volume is equal to, simplifying it, 75 pi h cubed over 4. All right, so let's just take the derivative of that now. So it's dV dt. That's all constant. That's 75 pi 4. So really it's 75 pi times 3h squared over 4. Okay, and that gives us dV dt is equal to 225 pi h. Oh, I forgot this dH dt. That's very important. Okay, over 4 dH dt. Okay, let's just kind of go over here and keep working this. dV dt. Now this is the deal. The water's falling. It's a little tricky sometimes, but the water's falling, so we're going to actually use as negative 50. Okay, is equal to 225 pi, and now we're going to use our value of h because we've taken the derivative already. You don't substitute in the beginning, because if you substitute in the beginning, it all just cancels out, and we have derivative of a constant, which is 0. That's like very, very bad. Okay, but it's 225 times h, which is 5 squared over 4, and of course dH dt. And then you guys can do all that work. I just divide everything out, and I wind up getting dH dt is equal to negative 32 over 9 pi, and of course this is then centimeters per minute. Okay, so you can tell me it's negative, so it's falling. It's dropping down, right? It's dropping. That height is dropping by 32 over 9 pi centimeters per minute. Okay, let's do B over here, because you're like, well, Mr. Curvis, man, you're barely in the room here. But guess what, math fans? Right? Didn't we relate these guys together? Right here. Look at this. Oh, this is so sweet. We related those guys together, which pretty much means I can just take the derivative of both sides. I can plug in my dH dt and find my dr dt, because that's what I'm looking for the next part. It's saying find how fast the radius is changing. Oh, that's pretty sweet. Okay, so let's do that. r is equal to 15 halves h. Take the derivative, it's dr dt equals 15 halves dh dt. Okay, and then plug it in. Dr dt equals 15 over 2 times 32 over 9 pi. And we get, it's actually negative, right? Negative 32. So we get dr dt, because the radius is shrinking too as it's going down the cone, right? It's equal to negative 80 over 3 pi centimeters per minute. All right, not too bad. Let's move on to the next one. Number 28 is particle motion. A particle P of xy is moving in a coordinate plane in such a way that dx dt is equal to negative 1 meters per second and dy dt is equal to negative 5 meters per second. How fast is the particle's distance from the origin changing as it passes through the point 5, 12? Okay, well, so let's write this out here. Dx dt is equal to negative 1 meters per second, and dy dt is equal to negative 5 meters per second. So if I sketch a picture in this corner here, I have this is my x value and this is my y value here. Okay, and my coordinate is 5, 12. So it's passing through that point, and what I'm doing is I'm trying to ask you guys the rate of change. Find how fast the particle's distance is from the origin is changing. So I'm looking for, we'll call this r. I'm looking for dr dt. Okay, so let's just plug it in. And what are we going to use here? Well, think about it. Isn't this Pythagorean theorem? Well, first of all, what is the value of r? Well, it's a 5, 12, 13 triangle, so it's 13. And again, you don't plug it in, right? What we do is we have x squared plus y squared equals r squared. Okay, you take the derivative first, then you plug things in. So this is all with respect to t. So do you guys agree it's going to be 2x, and then it's going to be dx dt plus 2y dy dt equals 2r dr dt. All right, and it's easy. Now I plug the stuff in. So it's 2 times x, x is 5, dx dt is negative 1, plus y is 12, dy dt is negative 5, equals 2, and then r is 13. We use that with the Pythagorean theorem, and then dr dt. Pretty easy, man. Okay, so we wind up getting negative 10 minus 120 equals 26 dr dt, and that's negative 130 divided by 26, so we get dr dt comes out to be negative 5 meters per second. That one's an easy one. All right. Okay, let's do, and again, that was 28. I didn't label that 28 here. Okay. Let's do the next one, 29. All right. A man 6 feet tall walks at a rate of 5 feet per second towards a streetlight that is 16 feet above the ground. At what rate is the length of his shadow changing when he is 10 feet from the base of the light? So let's draw a nice picture here, because that is definitely going to help out a lot. All right, so I'm going to label this man is 6 feet tall. The street light is 16 feet tall. This is the length. I'm going to call this Z. That's the length of the shadow. And I know you want to write down 10. I'm just going to write down X here for now. The reason I'm going to write down X is because I don't want to plug in the value of 10 right away, because it's kind of the same thing as before. If you plug in the value, right away and you take the derivative of it, you're taking the derivative of a constant, which is 0. You don't want to do that. Okay, so I'm going to wait until I take the derivative before I plug a 10 into here. And then, of course, my dx dt is equal to, I'm moving at 5 meters per second towards the light. So, it all depends on how you look at it, but I'm going to write it as negative 5 feet per second. All right. It all, again, depends on what your answer is. If you're saying you're walking towards it is positive, I'm saying walking towards it is a negative, and if I walk away from it, it's positive. Okay. Anyway, I am looking for, looking for dz dt. Okay, which is again, the question they're asking you is how fast is the particles, or sorry, at what rate is the shadow changing? And that's what the shadow is z. So what are we going to do here? We're probably going to come up with a ratio. You guys remember this from geometry, these types of problems. Okay, and what you're going to do is you're going to say 6 over 16 is equal to z over z plus x, right? That's that whole length. So it's the part over the small over the big equals the small, which is the z, over the big, which is z plus x. Okay, if I cross multiply, well, I can simplify this first before I cross multiply. So 3 and 8, right? So if I cross multiply now, I get 8z is equal to 3z plus 3x. And move that 3z over, I get 5z is equal to 3x. And now what I can do, I related the that distance, the z and the x together. Those are my only two variables here, right? Because those are the things I'm given. I'm given a dx dt is how fast he's moving, and I'm looking for how fast the shadow is changing. All right, and so let's take the derivative of it because I know dx dt. And if I do that, I get 5, and it's dz dt equals 3 dx dt, right? And I have all my information here. So 5 dz dt equals 3 dx dt is negative 5. And then I divide both sides by 5. So dz dt is equal to negative 3. That's it. So my answer is negative 3 feet per second. That's how fast the shadow is changing as I'm walking away. Now again, if I could have done positive, right? Some of you guys are going, well, wait a second, why didn't we do positive? I could have. And then what would have happened with that one? That would have been positive as well. So no big deal. Either way you look at it, as long as you give me the correct answer, you're good to go. All right? Okay, so let's, we've got a couple more to do here. Oh, I just want to make one mention here, math fans. I did not use the 10, right? I initially told you this is going to be 10 here. And I never used it because once I took the derivative, the value of x went away anyway. So that was not a, obviously not a known thing because think of these guys are side by side. So that's probably why it never even came into play here because they're side by side and it was not a big deal whether it's 10, 20, 50 or whatever. It didn't really come into play. All right? All right, so let's do number 33. All right, so number 33, it says, it's a building shadow. On a morning of a day when the sun will pass directly overhead, the shadow of an 80-foot building on a level ground is 60 feet long, as shown in the figure. Okay, at the moment in question, the angle theta the sun makes with the ground is increasing at a rate of 0.27 degrees per minute. At what rate is the shadow length decreasing? Express your answer in inches per minute to the nearest tenth. Remember to use radians. Okay, that's actually pretty important for this guy. You got to use radians for this. Really, use radians for any type of scientific or mathematical problem, any engineering problem. You're going to be using radians. So, if I make a quick sketch here, you got your building. Okay, your building is 80 feet. And first of all, I want you guys to realize that this is constant. That's not going to change. And of course, we got a nice right angle. You have your theta. And here it's x equals 60 feet. All right. And it's telling you that the theta is changing at a rate of 0.27 degrees per minute. So you got your d theta dt equals 0.27 degrees per minute. Okay, it's even telling you got to convert it into radians. So of course, how do you convert it into radians? You guys should know that. Pi over 180, right? And in a decimal, you're going to get 0.0015 pi radians per minute. That's d theta dt. So what you're looking for here, math fans, is you're looking for, so find dx dt. Okay, because they ask you, or the question is, at what rate is the shadow length decreasing? So write this line right here. That line's your shadow. Okay? So a couple things I can do. I know this hypotenuse, this is it's a 3, 4, 5 family triangle, right? So this is 60, 80, and then this is 100. I mean, you can always use Pythagorean Theorem, but that's 100 feet for that guy. All right. So let's, and you're like, well, why do we really need this? But let's come up with, we're trying to find dx dt. So do you guys agree I can write this as tangent of theta is the yax, right? Or it's 80 over 60. So tangent of theta is equal to, if I reduce that, it's 4/3. And the reason I'm doing that, because truly, let me write this out here. Tangent of theta is equal to 80 over x. Remember, you don't substitute that in, but the reason I'm doing this, math fans, is when I take the derivative of tangent of theta, what am I going to get? What's the derivative of tangent of theta? Isn't it secant squared? So let me actually write this. Secant squared of theta, d theta dt, is equal to, so let's keep going here. I can use the quotient rule, bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, so it's minus 80. The derivative of the bottom is just 1 dx dt, all over the bottom squared. So the reason I did this right here is because I need secant squared of theta, and if tangent of theta is equal to 4/3, just based on this nice triangle here, right? Isn't secant of theta is what? 1 over cosine, right? So it's going to be hypotenuse over adjacent. So it's 100 over 60. So simplify that. Secant of theta is equal to 5/3. So secant squared of theta, which is what we're going to use it here, is equal to 25 over 9. It's the whole purpose of doing that, is then I can write that as 25 over 9. Pretty sweet. Of course, d theta dt is 0.0015 pi radians per minute. So I can just say that over 1, right? And that's equal to negative 80. Of course, we're looking for dx dt over, and then our value of x is going to be 60. Now I plug it in. So 60 squared. So it looks a little messy. You got to multiply all that stuff out. I'm not going to do that here because you guys can do that. And I wind up getting dx dt is equal to negative 0.5890 feet per minute. Okay, but there one more thing here. We got to put it in inches per minute. That's what they're asking for. So we're just going to multiply this by 12 inches per foot, right? And so anyway, we wind up getting dx dt is equal to negative 7.1 inches per minute. Okay? So those are the related rate problems. We got one more problem here, and it's going to be on page 258. and it's number 46. So let me read off real quickly here. The area of a triangle. An isosceles triangle has a vertex at the origin and its base parallel to the x-axis with vertices above the x-axis on the curve y equals 27 minus x squared. So basically this is what you have here, and this is number 46. And this is your picture. And this is some curve going around here. And that curve is y equals 27 minus x squared. Okay, vertex looks like it's going to be 0, 27, but that's cool. So remember, this is x and x. Don't forget that. Don't just write one x there, and this is our y value here. Okay, and what I'm trying to do is I'm trying to maximize. It says find the largest area the triangle can have, so I'm trying to maximize the area. So you guys know an area of a triangle is 1/2 base times height. And now we're going to do it in terms of x and y. So area equals 1/2. Base is 2x. Height is y. All right. Once again, you need one variable here. Okay. Well, actually, let's simplify this. So isn't area is equal to now just x times y? Okay, that works out well. I need one variable, so I'm going to substitute that y in there. So again, area is equal to x times 27 minus x squared. So area is equal to 27x minus x cubed. And so we're going to take the derivative. A prime is equal to 27 minus 3x squared. Find our critical values. So 3x squared equals 27. X squared equals 9. So x equals plus or minus 3. Okay, and we know it's going to be positive 3, right, for a length. So x equals 3. And what we're going to do is we're going to do our interval testing, which you guys should know. We always have to do that. So if I pick, it doesn't matter. Let's pick 2 and 4. Okay, plug that into the derivative equation, right? So it's going to be 2 squared is 4, times 3 is 12, 27 minus 12. That's a positive value. Put a 4 in there. 4 squared is 16. 16 times 3 is 48. So that's going to be a negative value. So again, take your hand, goes positive to negative. So that makes it a maximum value. And so and do we have to test endpoints here? Well, let's think about that, because that's always been an issue now. Do you test endpoints? Well, no, because you can't have a 0 value for an x, can you? Because it wouldn't be a triangle anymore. So you can't have endpoints. Sometimes you have endpoints. Sometimes you have endpoints when you're talking about just numbers, but if I'm talking about an application problem for thickness of something, you don't have an endpoint, right? It's an open interval. But if I give you a restriction, and if I tell you it's got to be between this length and this length, then you have an endpoint and you want to check those. All right, so always be careful if there is an endpoint. Okay, if again you can't have a 0 width, but you can have an endpoint if I give you like I think the one question you've had before is the side of a barn, right? You can have an endpoint with that. Okay. All right. Anyway, x equals 3. Obviously, we need to find our y values. So we have y. We plug that into 27 minus 3 squared. So y is equal to 27 minus 9. Y is 18. And then, of course, our maximum area is going to be plugging back into the original problem, right? Right here, which is really this guy here, isn't it? So area is equal to 3 times 18. So area is going to be 54, and it's units squared. Okay, so that's it. All right, so it took a while to do all these problems because I wanted to be really detailed. with them, and hopefully you guys are good to go with related rates problems. But they can be tricky. You just got to practice all kinds of stuff, and you know, you got to get in terms of the variable that you have the information about. If you don't, try to write it in some other terms of other variables if you can solve for it. Okay, but there were a variety of problems that we had here. Anyway, that's it, math fans. Have a nice day. Adios. Goodbye.